All right, everybody. We used this closure Boolean expression last time to kind of show you how you might lean into these Boolean expressions to help you prove things. The way they're usually done is by proof by contradiction. So I'm just going to show you that in general, and then we'll kind of break that down into the parts that we're using. If you have a statement like A implies B, you can logically write that as not A or B. We already know that. And so what you would usually do in one of these proofs is you would assume that A is true, and then you talk about, because A is true, right? That means this thing is not true. That kind of forces this part to be true. And so usually in these proofs, what you're doing is you're holding one of these things to not be true so that you can prove the other one has to be a true statement. So you're making an assumption that one of these pieces is true, and because of that, you know that B must be true to satisfy your Boolean expression, and then you end up showing exhaustively that this can't happen, and thus our assumption must have been false, which is a proof by contradiction. Now, that's not very applied, and that probably doesn't stick in your head very well, but that's how these all work. So let's do a quick example, which is a little bit contrived, but it's kind of cool. So let's say that we know that 4.5 is not a natural number, which clearly it isn't. But then let's say we're not sure about 3.5. Okay? Let's say that's our situation. So here's how we're going to start. We're going to assume that I'll show you kind of the whole proof here. We're going to assume that 3.5 is a natural number. That's our assumption. We know that natural numbers are closed under addition. We know that 1 is a natural number from the definition of natural numbers. Line number 2 up here says that 1 plus 3.5 should be natural, since 1 is a natural number and 3.5 is a natural number, because we don't know about 3.5, but we assumed something here. 1 plus 3.5 is 4.5, which was given as an unnatural number, right? It's not natural. So our assumption must have been incorrect. Our assumption that 3.5 was natural is the only thing here that could have gone wrong. And if you look at our little yellow box here, right? We kind of forced this not to be true. 4.5 is not natural, which was a given. We forced this to be false as well, because 1 is a natural number, so this statement is false. And then that leaves us with only one conclusion, which is that 3.5 must have not been a natural number, which is great. So we assume something is true, and then we show exhaustively that it can't possibly be true. And so by contradiction, we get kind of the opposite of our assumption. Right? This is how all these proofs by contradiction work. They're really cool. Again, I'll point this out one more time. The contradiction uses the box that we were working on from last video as well. Right? We knew that 1's a natural number, which makes this false. We know that 4.5 is not a natural number, which this was the closure by addition, so it should have led us to a natural number. So we know that this is false, which leads us with only one conclusion, that this piece must be true, and that is the fact that 3.5 is not a natural number. Super, super cool proofs by contradiction. There's going to be a lot of those in theory of computation that lean on this sort of box and that sort of situation. Okay. I think we'll stop this video here, and then in the next video what we'll do is we'll tackle these proofs for specific closure related to regular expressions, and move on from there. Okay, that's all for now. As always, be kind to each other, be kind to yourself. See you next time. Bye.